Hello everyone, and a very warm welcome to this lecture on studying fundamental physics and cosmology using current and future gravitational wave detectors. My name is Martin Hendry. I'm a professor at the University of Glasgow in Scotland. You can see the university behind me on my virtual background. And I'm in fact a professor of gravitational astrophysics and cosmology at the university. And my interests span the big questions in cosmology about the origin and evolution of our universe. Questions about how big our universe is, how it began, why it's expanding, and how fast it's expanding. And in recent years, I've been working increasingly in gravitational wave astronomy, a very exciting new field of astronomy that has made some quite remarkable discoveries in the last few years. I'm a member of the LIGO Scientific Collaboration, which is the global team of scientists working with our colleagues in the Virgo Collaboration who have direct detections of gravitational waves from the merger of compact stars, black holes and neutron stars deep in the cosmos. So today, I'm going to tell you a little more about what gravitational waves are, how we have discovered them, and what we can learn about objects like black holes and neutron stars by studying the signals when those objects merge and produce gravitational waves that spread out through the universe. I will also take a look at what the future prospects are with detectors which are planned for the next years and indeed decades, both on the ground and also in space. Within the LIGO Scientific Collaboration, one of my roles is to chair our Communications and Education Division. So you see some of the activities here that we're involved in education and public outreach. We participate in science festivals and we give talks at science events all around the world. In the last few months, we've been doing all of these events online because of the global pandemic, but we are still reaching out regularly to tens of thousands of our colleagues and friends and telling them the very latest discoveries and discussing with them all aspects of gravitational wave astronomy. So I'll do my very best to answer any questions that people have today. We'll do that at the end of my talk. Of course, in such a large collaboration, we have scientists and engineers working on many, many different aspects of gravitational wave astronomy. I'm certainly not an expert in all of them, but I'll do my best to answer questions that you may have. So the story so far about gravitational waves is a truly remarkable one. More than 100 years ago, the existence of gravitational waves was predicted theoretically in Albert Einstein's general theory of relativity. We can think of gravity in Einstein's theory as a curvature of space-time, and gravitational waves are produced when there is a change in that curvature of space-time. So we sum this up by the neat phrase, matter tells space-time how to curve, and space-time tells matter how to move, which captures the idea that gravitational waves are produced by changes in the curvature of the space-time, which are in turn caused by changes in the distribution of matter in the universe. Now, according to GR, gravitational waves propagate through the universe at the speed of light. And although in principle gravitational waves are produced by the acceleration of any massive body, to measure them requires really compact and very massive objects. And even regular stars would not produce the kinds of space-time distortions that we could reasonably expect to measure. So gravitational wave detectors are seeking to measure changes in the curvature of space-time, and we do this using the separation of test masses in incredibly sensitive detectors to recognize when a gravitational wave has passed by the Earth, produced by a distant source, like, for example, the merger and collision of two black holes. The gravitational waves produce this distortion as a dimensionless quantity that we call the strain. So if you have two test masses separated by distance L, then the change in that separation will manifest itself as a strain signal. So we normally measure that as the fractional change L, and the strain signals produced by even violent events like colliding black holes are almost unimaginably small. And that really is the challenge which caused it to be about 100 years from the prediction of gravitational waves before they were detected. They were detected by the twin LIGO detectors in the US in 2015. I'm actually wearing a t-shirt showing the very first signal that we detected. We'll talk more about that in a few minutes. And the basic design principle of the LIGO detectors was that of a laser interferometer. In fact, LIGO stands for Laser Interferometer Gravitational Wave Observatory. And the arms are very long, they're about 4 kilometers long, which means that the laser beams passing along those arms, having first been split at a beam splitter, they travel a very considerable distance. They bounce back and forth from the mirrors at the beam splitter and at the end of the arms. And as a gravitational wave passes by, it causes a change in the interference pattern of the two laser beams sent along those two perpendicular arms. Now, there are two distinct polarization states of gravitational waves according to general relativity, and that's analogous to the polarization of light. It means that certain orientations of the detector will be more or less sensitive to the amplitude of the distortions caused by the gravitational wave. But if we think of a gravitational wave that's coming straight down on top of the detector, then the distortion pattern would be maximized in that case. And you would see it like the little cartoon shown on the right here. It would be a stretching and squeezing of space-time, causing a stretching and squeezing of the arm length within the interferometer's arms. However, the magnitude of that distortion, as I said before, is almost unimaginably small. We're talking about a change of order 10 to the minus 18 meters. That's a millionth the width of a human hair, even over arm lengths of order 4 kilometers long, like the two LIGO detectors in the US. This corresponds to a shift of the width of a human hair over the distance from the sun to the next nearest star, Alpha Centauri. This is a almost unimaginably small number, and yet the LIGO detectors are sensitive enough to measure those tiny changes. Now, one of the challenges, however, is that many other sources of disturbance can mimic or indeed swamp such a tiny signal. So one of the chief achievements, one of the most remarkable achievements of building these detectors is making them sensitive enough, but also isolated enough from other sources of noise to be able to pick out these signals coming from the cosmos. So in fact, when we made that first detection, we announced it some months later in February 2016. One of my responsibilities was to write the science summary to accompany our detection paper. And a key section of that science summary was to answer the question, how do we know that 150914, that signal, the first ever direct detection, was a black hole merger? So this is all about extracting information from the waveform that we observe. So what I'm going to do for the next few minutes is walk you through a simplified version of answering that question. We're going to look at the signal. We're going to use some high school or elementary undergraduate physics to try to see what we can learn about the properties of the sources that produce this change in strain, this strain pattern. We call it a chirp, and we're going to look at what information we can learn from analysing the chirp of GW 150914. Now, our collaborations wrote a paper on this in the summer of 2016. So in fact, you see that shown there, and I'm going to extract some details from that paper and just very briefly try to give you a flavour of how we can learn about the astrophysical properties of the mergers we observe. So the game plan for the next few minutes is to begin by estimating the gravitational wave frequency and how it changes from the data themselves, and then to use a very little amount of GR theory to relate the gravitational wave luminosity to the masses of the sources and also to their separation. And then we do that using some simple orbital dynamics, essentially just at advanced high school or elementary undergraduate level, to work out their separation. And that's really how we can convince ourselves that these had to be black holes. Okay, so let's begin with those waveform patterns themselves. And we can roughly estimate the gravitational wave frequency from just looking in the time domain signal at the separation of the peaks in that evolving pattern. So, of course, that's rather crude, but it does give us a decent way to estimate roughly what the gravitational wave frequency was. That's good enough for our purpose today. In fact, we can do slightly better if we represent the data a different way. This is called a spectrogram or a time frequency plot. So it shows that the frequency is sweeping upwards as the time advances, as we will see, as the two black holes get closer together and eventually merge. So let's make a rough estimate of the maximum frequency in our signal, which is what we associate with the moment of merger. So that's where the signal is brightest here, because the colours are representing the statistical power in the signal at particular frequencies. And let's make a conservative estimate of 150 hertz, 150 cycles per second. Now, we've got to start thinking about what's actually going on in the system itself at this point. And the gravitational wave frequency is in fact twice the frequency of the orbit of the two bodies around each other. So if we represent them as two masses, M1 and M2, separated by distance r, which is r1 plus r2, and there's an orbital frequency, an orbital angular frequency of omega, then the gravitational wave frequency will be twice the orbital frequency. So one way to see why that should be is that the distortion of space-time, the stretching and squeezing, is the same when M1 and M2 reverse their positions. And then, of course, it's also the same when M1 is back when it started. So the gravitational wave pattern will repeat itself twice as often as the orbital pattern. So now we need a little bit of general relativity. And again, I won't spend very long in the mathematics here, but I appreciate this might not be everyone's cup of tea, but just to give you a flavour of where the numbers come from. So what Einstein's theory gives us is a relationship between what's called the mass quadrupole moment. So that describes our distortion in the distribution of masses. And in fact, it's the second time derivative of that. And that maps directly to the perturbation in space-time itself, essentially what we call the gravitational waves. But the key point here is that there's a constant of proportionality out front, and that involves the gravitational constant from Newton's theory of gravity, big G, about 6.67 times 10 to the minus 11 in SI units. But look, we're dividing that by the speed of light to the power 4, which is a really, really big number. And then we're also dividing it by what's called the luminosity distance to the gravitational wave source. So what all of that means is that even if you have a very strong distortion in the distribution of mass on this right-hand side, it's going to produce a very small distortion in space-time, in the curvature of space-time. That's why gravitational waves are so hard to measure. So just cranking through some of the maths, again, just giving you the highlights here. All the details are in that basic physics paper that I mentioned a few slides ago. What GR also says is that if we integrate that metric perturbation, well, actually it's its derivative squared, then we can relate that to the luminosity in gravitational waves. So that's the rate of change of gravitational wave energy from the system. So we have to define a few things, but in fact, this mass quadrupole moment, if we just have two masses orbiting each other, is fairly simple. So that mass quadrupole moment can be calculated in terms of the properties of these masses, their separation, and then we plug all of that in, we do a bit of algebra, and in the end we get this equation here, which tells us the rate of change in time of the gravitational wave energy, and it relates that to the 6th power of the orbital angular frequency, and also to the 4th power of the separation of the two masses. And again, there's this incredibly small number, big G over c to the 5. So that tells us that the gravitational wave luminosity, dE by dt, is going to be very small. But we still, even before the first gravitational wave detection, had good indirect evidence that gravitational waves are indeed being emitted in this way as two massive bodies spiral in towards each other. Because from the 1970s onwards, observations of a binary neutron star system known as the binary pulsar by these two chaps here, Russell Hulse and Joe Taylor, what that revealed of these two compact stars was shrinking. So this was noted with radio waves, but this was an indication the reason for the shrinking was the emission of gravitational waves. But the gravitational waves from this system were too low frequency to be detected directly. It would take detectors like LIGO and Virgo to be able to do that. But what we could do was at least be confident that general relativity was indeed correctly predicting that such systems would shrink as the gravitational waves are radiated away. So the orbit shrinks because it's losing energy, and that energy is radiated away in the form of gravitational waves, according to the equations we saw a couple of slides ago. So now what we can do, just to tie some things together, is we can use the notion of the orbit of these two massive bodies around each other. Actually, we can make do with just the Newtonian expression for the orbit for our purposes today, and we can relate that orbital energy to the gravitational wave energy, or in particular, the rate of change of the orbital energy to the rate of change of the gravitational wave energy. In other words, the gravitational wave luminosity. So that's what's shown here. And if we also use Kepler's third law of orbital motion, then that allows us to, in turn, bring in a relationship involving the separation of the two masses. So again, there's a bit more algebra to be done, but doing all of that algebra gives us eventually, after a number of lines, this rather complicated equation looking here. So what it says is that omega dot, the third power of omega dot, that's the time derivative of the orbital angular frequency, can be related to the orbital angular frequency itself, to the 11th power, times a quantity involving this curly m that we call the Chirp mass, which is a function of the masses of the two objects in the system. So still a bit more algebra to do. We can rearrange that equation to get the Chirp mass on the left-hand side. And that basically tells us that if we measure the gravitational wave frequency, because I've now replaced omega by f gravitational wave, and the derivative, the time derivative of the gravitational wave frequency, then we can estimate the Chirp mass, because everything else on the right-hand side is a constant of nature. So what we get then is an equation that lets us estimate the Chirp mass, but if we do a little bit more work, we can get it in a simpler form, because it's quite hard to measure f dot directly from the graph, but this is a separable differential equation. So if we integrate that, then what we get is that this power of the gravitational wave frequency is just proportional to time, Tc minus T, where Tc is the coalescence time of the two black holes. Well, we don't know the black holes yet, but we're just about to find that out. And the constant of proportionality involves this Chirp mass. So we can read the frequencies from the time frequency plot, match them to the left-hand side, and then basically make a plot of that as a function of time. So that's what's shown here. And also shown is some straight lines that correspond to different values for that Chirp mass. And even if we are a bit on the conservative side, what we can see from this is that the Chirp mass seems to be at least 30 times the mass of the Sun in order to match these data points extracted from the time frequency plot that we saw before. Now, if we go with that 30 times the mass of the Sun and further assume that the two masses are actually the same, then if the Chirp mass is 30 solar masses, that means that the individual masses are actually 35 solar masses. And moreover, we can then use Kepler's third law to estimate the separation of those two masses. And what we get is a remarkably small number. We get 350 kilometers. So our event was producing a signal from two massive objects more than 30 times the mass of the sun, and yet separated by only 350 kilometers. So to be frank, the only objects we know of that could be that massive and that close together are black holes. We can see here that the Schwarzschild radius of a black hole of mass m is 3 kilometers times the mass in masses of equal to the mass of the sun, solar masses. So we're talking about two objects with a Schwarzschild radius of about 100 kilometers each, and they are separated by only about 350 kilometers. That was our first event, and that's why we were so confident in calling this out as observation of gravitational waves from a binary black hole merger. So here's showing a kind of reconstruction of what space-time was doing as these two black holes merged with each other. And just as the black holes merged, there's a burst of gravitational wave radiation emitted. And in just a small fraction of a second, more than, well, perhaps even as much as 50 times the luminosity in light of every star and every galaxy in the entire universe was radiated in the luminosity of gravitational waves. So this was our first event, a spectacular new dawn of gravitational wave astronomy. And maybe some of the other talks in this series have already covered aspects of this in great detail. So I'm not going to say much more about our first event, but we've used it as a kind of laboratory to understand how we can extract information from analysing the waveform. Of course, in reality, we do that using much more sophisticated methods than the simplified analysis I presented today, but hopefully just going through using nothing really more than elementary undergraduate physics has helped you to see where some of these numbers come from. So our analysis that was done more rigorously produced the results shown here. What we got as the masses of this GW 150914 event was about 29 times the mass of the sun and 36 times the mass of the sun merging together. So not so different from our crude estimate using simplified physics. And we also found that the waveform did indeed match very well the predictions of general relativity. But a whole lot more has happened since that very first detection. Firstly, in August 2017, just over 3 years ago, August 1st, the Virgo detector began operating in its advanced configuration. The LIGO detectors had been upgraded to advanced LIGO between 2010 and 2015, but then advanced Virgo came online a little bit later. Now, having 3 detectors was hugely beneficial in determining the sky position of the gravitational wave sources. And in fact, within just 2 weeks of the operation of advanced Virgo, we had already seen the fruits of that. On August 9th of 2017, for example, a binary black hole merger was observed. And then again on August 14th, a binary black hole merger was observed and was actually localized in the sky reasonably well to about 60 square degrees on the sky. And here you see that event from the 14th of August 2017, and its sky localization was hugely better than those earlier events shown, which were observed by just the twin LIGO detectors in the US. So just 3 days later, on August 17th, 2017, we had an even more remarkable discovery. This was this time the merger of 2 neutron stars, and this time it was accompanied by gamma rays. So this was our first multi-messenger event that was observed in both gravitational waves and light. And in fact, it was observed across the entire electromagnetic spectrum, all the way from gamma rays to radio. And in optical, it was seen as the aftermath of the merger, what we call a kilonova, shown here in this galaxy NGC 4993. This crosshair here is indicating where the kilonova was observed just a few hours after the gravitational wave event. Now, this allowed us to do what the remainder of my talk is going to focus on, which is using gravitational wave sources as probes of cosmology. Because what we were able to do, using essentially the methods that we described in the first part of my talk, we could estimate the chirp mass and indeed the distance from analysing the amplitude, the frequency, and the frequency derivative. And that would give us a distance to the gravitational wave source that we could combine with a redshift to its host galaxy. So the basic framework and structure for doing cosmology using what we call standard sirens was first laid out in the mid-1980s. And it was really astounding to think that just about 30 years later, we were actually able to do this for the first time. Now, there is a bit of a catch, because what we get from analysing the gravitational wave data is in fact not the chirp mass itself, but what we call the redshifted chirp mass, the chirp mass multiplied by 1 plus the redshift z. And that means that we need to get the redshift from something else. We don't get that from the gravitational wave data, but we get it either from identifying an electromagnetic counterpart of the gravitational wave event itself. That's what happened in 1708-17. We saw the kilonova, or getting the redshift of the host galaxy. But that means we've still got to know which host galaxy is the correct one. So for 1708-17, that was easy. We found the kilonova, we had the host galaxy, we could get the redshift. That allowed us to estimate what we call the Hubble constant, the expansion rate of the universe. And our value, what we call the posterior distribution for the Hubble constant, is shown by this blue curve. And well, it's not terribly precise. And that's because, of course, we have only one such event that we're using. And consequently, from this single event, we were not able to really solve a mystery that there's been in cosmology in recent years, which is a disagreement between the measurements of the Hubble constant by different methods. So if we use methods involving distances to nearby objects, things like supernovae or Cepheid variable stars, then we get values of the Hubble constant round about 67, 68, shown by this green band here. Shown by this orange band, slightly higher, about 73. And if, on the other hand, we use very distant information from what's called the cosmic background radiation, and then reverse engineer what the value of the Hubble constant is, then we get values in the green band, about 67 or 68 in the appropriate units. And these values don't agree, and that's a real puzzle. So it's hoped that gravitational waves might help resolve that puzzle, but you're not going to do it with just one event. But nonetheless, it was very satisfying and very encouraging that at least this first observation and first determination of the Hubble constant was consistent with the different methods using electromagnetic data, albeit that those methods don't seem to agree very well with each other. The basic problem is the big uncertainty in the Hubble constant, and a large part of that is coming from this tail, from this long tail here, which is to do with, in large part, not knowing as precisely as we would like the inclination of the gravitational wave source to our line of sight. And I'll come back to that in a few slides' time. I should mention, though, that we can also, in principle, measure the Hubble constant even if there isn't an explicit electromagnetic counterpart. And the idea is, let's say you've got two black holes that merge, you don't see any associated EM signal, but if you can localize those black holes well enough on the sky, there might only be a handful of galaxies that could potentially be the host galaxy. So what we can do is we can fold into our analysis to get the Hubble constant a kind of averaging, or what we call marginalizing, over all of those possible host galaxies. And that's been done, firstly, for that event 1708-14 that we mentioned, the one that was observed with Virgo and LIGO in August of 2017. But that doesn't really give us a terribly good value of the Hubble constant, but it's a good proof of concept. And the problem was the sky localization wasn't that good, and there were a lot of galaxies that could have been the potential host galaxy. Now, a better way to do it is to combine all of our gravitational wave observations. And since 2015, we've confirmed the detection of a whole number of binary mergers. One neutron star merger prior to 2020, the one that we talked about before in 2017, and also a number of binary black hole mergers. So if we call these dark sirens, because there's no EM counterpart, those binary black hole mergers can still, in principle, give us a good estimate of the Hubble constant. So that's an analysis that we've attempted, we've carried out. Again, because we haven't observed so many binary black hole mergers yet, we don't actually get much improvement on our Hubble constant estimate over just using the binary neutron star. So that's the orange curve. It still dominates our estimate of the Hubble constant. But nonetheless, as we observe more and more binary black holes in the future, this sort of analysis will get better and better. So talking of the future, I now want to spend the final part of my talk looking at what we've learned in the very recent past and how that will shape the development of the field in the coming years. So we've talked so far about the first detection, and we've talked about the binary neutron star merger in 2017. But up to August 2017, we in fact observed a total of 10 binary black hole mergers plus the neutron star merger. And in December of 2018, we published a catalogue of all of those events. So we call this our GWTC1, Gravitational-Wave Transient Catalogue 1. And we were able to use all of those events to carry out a number of analyses. So I've mentioned the dark siren analysis to get the Hubble constant. Another analysis we did was to test general relativity. Now, this is a rather complicated looking diagram. I'm just going to talk briefly about the left-hand side, because what we were doing here was doing an analysis of the waveform before the merger, what we call the in spiral, and the merger itself. And we can estimate from that what the final mass of the black hole that's left behind when the two black holes merge should be. And then we can do the analysis of the final part of the waveform using the actual data themselves. It's called the ring down, and that can give an estimate of the final mass as well. And we can do something similar to do with our estimates of the spin of the black holes, the two spins separately, and then the spin of the combined black hole. So what you see here is a quantity to do with the difference between the final mass that you estimate from the data themselves and the final mass that you predict using the first part of the waveform and assuming that general relativity is correct. And then in the vertical axis, it's the same deal, but to do with the spin. And the point is, if general relativity is the correct theory, then those two analyses should agree with each other. And therefore, the differences should be very small. And indeed, you see that from analysing our first catalogue, that was in fact the case, and that the differences in the final masses and the final spins were consistent with zero. So that is an indication that general relativity is passing the test that we're subjecting it to using our gravitational wave data. It doesn't mean that general relativity is definitely the correct theory. It just means that we haven't found any problem with it yet. And of course, we would like to do analyses like this, and also the one on the right, which again, you can read the paper to find out more about that. We'd like to do those analyses more thoroughly in the future. So how is that going to become possible? Well, firstly, there's events that we have as candidate events that were detected after the ones that feature in our first catalogue. And those come from our third observing run. That began on April 1st of last year and ran through to March 27th of 2020. And during the third observing run, the LIGO detectors and the Virgo detector were made more sensitive due to a variety of upgrades in their performance. You can find out more about that in our LIGO.org webpage, where there were news items at the time that the runs began. And increasing the sensitivity meant that we could detect sources at greater distances. And sure enough, during the third observing run, the rate at which we saw candidate events rose rather sharply. So by the end of the third run, we had a total of 67 either confirmed events from 01 and 02 or candidates from 03. And really, over the last many months, we've been carrying out analyses to try to determine how many of those candidates we can in fact confirm as gravitational wave events. So we've already confirmed a few. In January of 2020, we confirmed that one of those events, which was observed on the 25th of April 2019, is, we believe, a second collision of binary neutron stars, a second collision of a pair of neutron stars, the same sort of event as 1708-17, but this time without an electromagnetic counterpart. There could be many reasons why that EM counterpart was not observed, probably the main one being that this event was quite considerably more distant than 1708-17 was. And in fact, we think that this binary neutron star collision has produced perhaps an object which is probably a black hole, but what it indicates is that that binary neutron star pair was the most massive pair of neutron stars that we've observed so far, certainly more massive than the neutron star pairs observed with radio telescopes in our own galaxy. So that's opening up a lot of interesting questions about how these neutron stars might have formed. And then in April of this year, we announced another gravitational wave event, this time a candidate that was detected in April of last year, on the 12th of April to be precise. And we confirmed that this was a binary black hole merger, but this time with more unequal masses than any we had reported up until that point. So here's a little animation of that. And what's interesting about having the unequal masses, the most massive one in the pair is about more than three times more massive than the lighter companion, is that it subtly changes the gravitational wave pattern that we observe. And what we get is what are called higher order multipoles in the signal. Think of them like higher harmonics in a sound wave. So if you have higher harmonics in a sound wave, it changes the character of the sound. It makes it a richer, fuller sound. And in the same way, having these higher harmonics or higher multipoles allows us more rich information about the source themselves. Now, in one case, the case of 1904-12, what we see here is the way in which that gives us more information about the distance than if we just use the dominant multipole, the main signal that is dominant, particularly when the two masses are close to equal. And this takes us back to that long tail in our estimate of the Hubble constant. So that long tail is because of not knowing the inclination so well of that system, but measuring the higher order multipoles allows us to estimate that inclination better. That's represented by this angle here. And the blue curve indicates that this was rather uncertain from just the dominant multipole, which in turn means that the distance is rather more uncertain. But using the higher order multipoles, and indeed also information about the precession of the source, that uncertainty. And all of that could be very important in fitting the Hubble constant from here, August 2019, 1908-14. And this is an interesting one because it's an even more imbalanced pair. It was a pair of black holes or a black hole and a neutron star. And that's the interesting aspect of this. We don't know whether the lighter companion was the most massive neutron star we've observed to date or the least massive black hole. So those questions associated with 1908-14 are discussed on our website and in the paper itself, of course, but feel free to take a look at that afterwards. So in my final 10 minutes, let me just briefly touch on what lies ahead. So the third observing run ended in March of this year. We were always planning to end it in the spring of this year because the next stage is to improve the sensitivity of the detectors even more. We anticipate coming back online in somewhere between 12 and 18 months. And that will be with our fourth observing run, where hopefully we'll be seeing events every few days. And also, on a similar timescale, we expect that the KAGRA detector in Japan will commence operations. In fact, it actually began some initial operations a few months ago. And then looking slightly further down the line, there will be a LIGO detector in India. So LIGO India is slated to begin operations in perhaps a little over 5 years. And here's an artist's impression of what will all be happening at LIGO India when the construction is complete and the detector is operational. Now, having those extra detectors is hugely advantageous for estimating the parameters of the gravitational wave sources and actually just determining where they are on the sky above all. And it's all because you can triangulate better when you have those extra detectors. So here's from a study from a few years ago where we can see that having LIGO Hanford, LIGO India, KAGRA, LIGO Livingston and Virgo, we get sky localization areas which are typically very much smaller than if you just have, for example, LIGO Hanford, LIGO Livingston and LIGO and Virgo. So having that global network of detectors will really help us to pin down where our sources are and to determine their properties. And moreover, the detectors are going to be upgraded further beyond the design sensitivity that was always the target for advanced LIGO. So we've kind of pushed the envelope a little more, and there's now a program ramping up called Advanced LIGO Plus or A+, and LIGO India is going to come online in the A+ configuration. And with A+, that will give us a much greater reach than we've had in O1 and O2, such that we reasonably can expect to get sources virtually every day. And that will give us such a substantial data set that many of the questions that we want to begin addressing, to do with the Hubble constant, to do with analysing the population of black holes and understanding their formation mechanisms, will become much more possible with Advanced LIGO Plus. But in fact, alongside that, what's equally important is developments happening on the electromagnetic side. So on the timescale of Advanced LIGO Plus, we're going to have operating the Large Synoptic Survey Telescope, or recently renamed the Vera Rubin Observatory. And this is a remarkable instrument that's going to see large chunks of sky to very great distance and is going to produce huge amounts of data. And within those electromagnetic data, we'll be looking for the EM counterparts of our gravitational wave events. And that's going to help enormously with finding, for example, kilonovae and neutron star mergers. So it's not just the developments on the gravitational wave side, which are very exciting, but also the corresponding developments and upcoming projects on the electromagnetic side. LSST is just one. There are several others across the EM spectrum. So this plot from a paper written by some of my LIGO colleagues just a few years ago highlights what comes ahead in terms of measuring the Hubble constant. And the bottom line here, quite literally, is this green curve, which is anticipating how well we might measure the error on the Hubble constant on the timescale of LIGO Hanford, LIGO Livingston, Virgo, KAGRA and LIGO India. And we're looking at the potential to measure the Hubble constant to about 1%. And that could go a long way to solving that puzzling discrepancy between the Hubble constant measurements we get by more traditional methods, which people are referring to as the Hubble tension, underlying a lot of current cosmology research. But looking in my final few minutes, even further ahead, there's the prospect in the 2030s to probe even deeper into the universe, because even Advanced LIGO Plus will only allow us to probe a very small part of the universe. And looking ahead to the third generation of detectors, as they are referred to, we have the prospect to go much deeper and to see gravitational events across cosmic time. So there are two projects developing rapidly, one led by Europe called the Einstein Telescope, another led by the US called Cosmic Explorer. And in both cases, the goal is to achieve sensitivities about 100 times better than LIGO initially was, or about 10 times better than Advanced LIGO. And that means you're going to be probing 1,000 times more volume of the universe, roughly, than Advanced LIGO. And that should, in turn, give us 1,000 times more sources to detect. And all of that will hopefully help us move beyond just measuring the Hubble constant with gravitational wave sirens and start to tackle an even deeper question about the expansion of the universe, what we call dark energy. The dark energy that seems to be driving the cosmic expansion to accelerate, but fundamentally we don't really know what dark energy is. So there are various theories around, in fact a whole barrage of different theories, and often they can be characterized in terms of what's called the W parameter that relates the pressure of the dark fluid to its density. So if you have dark energy in the form of a cosmological constant, an idea that goes all the way back to Einstein himself, then that would correspond to W equals -1, but it would be a constant W. But dark energy could also be evolving, and we'd like to map how W evolves as a function of redshift to help us understand its true nature. So from third generation ground-based detectors, various groups around the world, including our group, have been looking at the prospects for constraining cosmology using those detectors, and in particular for measuring this W parameter and how it evolves with Z. And all these graphs really are telling us is that we're in the game, because the plots here are showing a comparison between predicting how well gravitational wave sirens will do and how well other cosmological probes, like they're called baryon acoustic oscillations or high redshift supernovae, there's a whole bunch. Well, as you can see from these plots, the constraints are broadly similar from gravitational waves that they are from the other cosmological probes. So it's always useful to carry out analyses like these using as many different probes as you can. So gravitational waves surely will have something to contribute here. There might be a very significant multi-messenger challenge, however, because what we want to be able to do for these sources is to observe electromagnetic counterparts, or at the very least to identify host galaxies. And that's going to be tough. So that's going to need telescopes like the Vera Rubin Observatory, and indeed even telescopes that come after that to accompany the gravitational wave analyses. And then very finally, there's also the prospect to do all of this from space, because there's a gravitational wave spectrum, just like there's an EM spectrum, and there is a mission to detect gravitational waves from space called LISA, which is a joint ESA and NASA mission led by ESA, and it's slated for launch in the mid-2030s. And LISA will also be able to shed, well, not light, but shed gravitational waves on questions about the nature of dark matter and dark energy. And just like with the third generation ground-based, the key here is to observe strong signals from massive black hole mergers. This time it's going to be supermassive black holes in the hearts of galaxies, but observed to very high redshift. And that will give us exquisite new ways to test GR, and also will give us new ways to probe the evolution and nature of dark energy. So all of this might help us, we hope, to answer this deep question: why does 95% of the universe appear to consist of strange matter and energy? So in my talk today, I've given you just a very brief overview of some of the things we can learn about gravitational waves, taking 10 answers if I don't get through them all today. So let's see, there's a whole number have been listed. Let me try to see what I can begin with. Right. So we've got a question from Sanjay Jaswant Sohani. Can we think of space-time as a material medium or as a sort of just mathematical model? That's a great question. I mean, there's a really deep philosophical nature to that. You know, is space-time a thing? Is it a material medium? But let me just point you towards one aspect of it, which is very important. And it's to do with the strain that we saw in the equations near the very beginning of my talk. And I mentioned a few times the very, very small value of the constants that were the constants of proportionality in the equations. Remember, we had g over c to the power 4th, and then later we had g over c to the power 5. So it's precisely because those numbers are so incredibly small that we need very compact and massive and dense objects to produce measurable gravitational waves, things like black holes and neutrons. And another way of saying that is that space-time is incredibly stiff. So if you think of space-time as a material medium and then analyze it using things like Young's modulus, one of the concepts you learn about in undergraduate physics, then you deduce that the Young's modulus of space-time is unbelievably high. And there's a very good YouTube video I can point you towards that explores that idea in more detail. The next question is from Blesil Kunju. How are gravitational waves different from other forms of waves known to us? Again, I'll try and be brief here, but this is a great question as well. They're different from electromagnetic waves in that they are quadrupolar. That means that, yes, they're transverse, just like EM waves, but they involve a stretching and squeezing. So you saw the animation near the top that was showing the stretching and squeezing of the detector, mirroring the stretching and squeezing of space-time itself. And that's different from the transverse wave behavior and sort of sinusoidal behavior of an EM wave. But there's other key differences too, to do with the polarization states and the angle between the polarization states. So let me not go into the details of that. Again, you can find much more on our website. But let me highlight just the second part of your question about the speed of light, because the electromagnetic waves from the kilonova and the gamma ray burst that preceded it, those arrived on Earth on August 17th, 2017. And the gravitational waves arrived at almost exactly the same time. And in fact, we believe that that's because they were emitted slightly earlier. And then there was a 1.7 second delay before the gamma rays were emitted. But henceforth, the gamma rays and gravitational waves travel towards us at the speed of light. They travel at the same speed. That's a prediction of general relativity. It's not an accident. It's a prediction that's hardwired into the theory. But this events like 1708-17 offer us a way to test that prediction. So to the best of our knowledge and to a very high precision, we believe that gravitational waves do indeed travel at the speed of light. Besides laser interferometry, is there any other method to detect gravitational waves? Let me briefly mention just two. We can use pulsars in our galaxy as a galactic scale gravitational wave detector. And there's a lot of work going on in that area. It's called pulsar timing. It's a fascinating field as well. And many of my LIGO colleagues and LISA colleagues also work on those analyses. I don't myself, but the methods of analysis are rather similar. But instead of using laser light, we're using the timing of the arrival of the pulses from pulsars. So again, take a look at that. The collaboration called Nanograv have tons of great resources for education about how pulsar timing works. There are other methods using the bulk properties of a big bar, a bar of metal, maybe aluminium or some other metal. And early ground-based detectors used the idea of the ringing of a bar as the sign of a gravitational wave passing by. But laser interferometers allow a much greater frequency range over which they can be used, and they're also more sensitive. So the bar detectors are not nowadays at the front line of gravitational wave research. Why does the stretching and squeezing of space not change the wavelength? But it does. Now, I'm not going to answer this in detail. It's a superb question from Chayan Chatterjee, but I will send on a link to a short paper, and there's like LIGO India come online in the coming years. Because essentially what we're really looking at there is working out how probable it is that a gravitational wave event could encounter, let's say, another pair of black holes as the gravitational waves propagate towards the Earth. And one of the things that could do is cause the gravitational wave event to be lensed. And there's a number of scientists working within our collaboration, and in fact, in particular, within LIGO India, who does. But remember, we're actually talking about a very small scale here. We're talking about only 350 kilometers apart. So all we need to be true for Kepler's law to hold on that scale is that the gravitational constant, big G, is the same everywhere. And that's very much underpins all of the astrophysics that we do, even outside of gravitational wave astrophysics in fields like exoplanets or studying binary stars. We deduce the properties of those systems by assuming that gravity works the same there as it does here. Now, as the objects get even closer together, you eventually have to replace Newton's gravity and Kepler's laws with the Einsteinian equivalents. But as you saw, we can still go a long way to estimating the properties crudely using Newtonian physics. And that's the whole point of the first part of my talk and the whole point of that basic physics paper that I highlighted from August 2016. Unik Segupta, has LIGO detected any presence of primordial black holes yet? Short answer is no, but we're certainly looking, and that's a really interesting topic as well. We would like to understand more about dark matter. I talked a bit about dark energy and probing W as a function of Z, but I rather ignored the equally mysterious topic of what is dark matter. And one plausible explanation for dark matter is, in fact, that it's black holes, it's primordial black holes. Now, it's not probably the most popular explanation for dark matter, but it is certainly still viable if one takes an open mind, if one looks at the constraints and recognizes that there's, a long way to go before we can really nail this down. So it's certainly sensible to go looking for primordial black holes. And there are several papers that I can point you towards which explain the constraints that we've been able to place on the population of possible primordial black holes from analysis of LIGO data so far. And the follow-ups to the question sort of talks about ways in which such observations might be rendered difficult, and those are all good points, but again, those are discussed a bit more in the paper. Now, we're technically out of time, but I think there's probably lots more questions to come. So let me just check with my hosts here that it's okay to run on for a little bit longer. As I said, I promise to answer questions by text later, but I'm more than happy to do it verbally as well. So let's go on a little longer and hope that my voice doesn't give up just yet. So the second broad class of topic was on career questions. And there's a nice question here from Mugesh Mohasundharam. I'm presently an MSc student. How can I start research in the mathematical model of GR? Well, that's a great question too, because it's important to emphasize that a lot of the work done within the LIGO collaboration across the world and Virgo too is done by undergraduate or postgraduate students. So I have a number of PhD students with whom I work. I also have, at the moment, I have 5 different MSc students who are working on different aspects of gravitational wave data analysis. So they are doing MScs through the University of Glasgow. So wherever your host institution is, if your MSc is in an appropriate field, and it doesn't have to be astrophysics, it could be many different aspects of physics to do with lasers, materials, or to do with even computing science and data analysis methods, talk to your supervisor. There could be a chance to get some project work related to gravitational waves. It's absolutely the case that you can begin to learn about all of this and to contribute to it at master's level. That's one of the things I tried to illustrate by the beginning of my talk and walking you through some of the things we can learn from gravitational wave sources using just undergraduate level physics. But let me move on to the next group. And yeah, I think there's a whole bunch here, but I'll just take a few. And then again, I promise to answer the remainder later. But let's take the first one. This is from Fazio Rahman. Has any lambda CDM model information been included to estimate the value of H0 equals 70 using GW 170817? That is a great question. From 170817 itself, because it was only 40 megaparsecs away, then the relationship between distance and redshift so nearby really is independent of the other cosmological parameters that you're alluding to, like omega mater, omega lambda, and so on, or other parameters that might be relevant to different flavors of cosmology. So for 170817 itself, then the answer would be no. But the dark side in analysis that I briefly mentioned, using all the binary black hole mergers and then marginalizing over the possible host galaxies, some of those binary black hole mergers were more than a gigaparsec distant. So really they are beginning to require us to think about the other cosmological parameters. So in the paper I showed in my talk, we assume the standard values for those other parameters from recent analyses of the cosmic background radiation by Planck, for example. But one could consider other values too. And again, the methodology that we use, known as Bayesian inference, is well equipped to deal with all that. You can marginalize over the other cosmological parameters to make sure that you're not kind of biasing your analysis to be dependent on particular choices. But looking even further ahead, there will, we very much hope, in the era of third generation detectors, or maybe even sooner, be the possibility to estimate both the Hubble constant and those other cosmological parameters simultaneously. In fact, I've been doing some work with a master's student of mine in Glasgow. Well, in fact, she's now doing a PhD in Canada. And we put a paper, and this was to do with LISA. We put that on the archive a few months ago, so I'll forward a link to that. You can look at that. And this is a paper considering how with future LISA observations, we might be able to constrain not just the Hubble constant, but also other questions like, are there more than 4 space-time dimensions? So that's looking at non-standard cosmological models. And many other scientists working in LISA or in LIGO and Virgo are doing similar things. They're asking questions about how well siren observations might be able to answer these puzzles in the future. Right, let me just mention one more. My final question then. Can we determine the angular speed of black holes at the time of merging? If yes, how much is it? This is from Vishnu Naiputa. And this is a great question too. And in fact, I think I'll share my screen again, if I may, and just to spend one more moment going back through one of the early slides in my talk. And it should just take a couple of minutes, but it is, again, a very neat question and a nice one to end on. So let's give you a quick recap of the talk in reverse as we zoom back through the slides to where we had reached as we were looking at this plot just coming up now. Oh, I've gone too far back. We're almost there. There we are. Right, so in this slide, what we've got is the two masses, and they're orbiting with a Keplerian angular frequency. And remember, I was answering one of the other questions. I was saying that, yes, this is not the full GR solution, but we don't need to go all the way to the GR solution yet. We can still learn useful things just from the Newtonian version. And from Newton and Kepler's third law, remember Kepler's third law, there we are, there we are, relates the angular frequency of the orbit to the separation. But the gravitational wave frequency, as I explained during the talk, is exactly twice the orbital angular frequency. So the angular gravitational wave frequency is twice the orbital angular frequency. So if we are talking about a gravitational wave frequency of 150 hertz, then that means, I'm sorry, this is a little bit slow, but it will catch up on your screen very soon. There we are. Okay, let me stop it there. And this was our estimate of a gravitational wave frequency of 150 hertz. So that corresponds to an orbital frequency of 75 hertz. So that means the black holes were orbiting around each other 75 times every second. And that's, you know, pretty mind-blowing. These are objects 30 times the mass of the sun, roughly, and they're going around each other 75 times a second just before they merge. You know, if you have a spin washing machine, talking about two masses of about 60 million kilograms going around each other at that frequency. So it's no wonder that this produces enough of a disturbance in space-time to generate gravitational waves that we can measure. So even though the gravitational waves are incredibly weak, we are shaking up space-time so violently when these black holes merge that it produces a signal we can detect. So on that note, I will stop. I'm so sorry I didn't answer all the questions verbally, but I'm sure my LIGO India colleagues will pass on the remaining questions, or actually I have them already, and I'll be more than happy to answer them in written form, and we'll get them back to you. So many thanks to everyone again. It was great to see so many participating, and please do find out more about the exciting future of gravitational wave astronomy. Bye, everyone.